Using Euler methods to approximate the solution for the initial value problem. Euler's methods approximate the solution for the initial value problem y prime equal to f, a function of xy, so fxy, y at the time x0 equal to y0. So in general, we do not know how to solve this one, and we try to approximate it as best as we can. So in this case, we use the Euler's methods. Assume that the actual solution curve look like this. So this is the curve, solution curve. The actual one is contain the points x, y, right? Any points living on this actual curve satisfy this initial value problem. In this case, they give us this condition, x0, y0. So let me pick that here. Let me just draw here from x0, y0. So we will try to approximate other points on the curve starting from this point. How can we do that? We use linearization. So in calculus, we can even approximate better using Taylor's polynomials. But we only use that until the degree 1. So let's say we have a curve gx, and we have the points x0, y0 on this curve, and then we will approximate this every point on the curve by around the neighborhood. So gx approximately g at 0 plus g prime at 0 x minus x0. Yeah. So here's y0 is g at 0. And then if you want to do more degree, you would have plus 1 over 2 factorial g double prime x0 x minus x0 square 1 over 3 factorial g triple prime x0 x minus x0 cube, and so on. We don't need that. We only need linearization. I only use until here. So we will approximate the red curve by this tangent line. So Taylor's polynomials here, we only approximate that. So this tangent line passing through this point, and the slope of the tangent line, slope of this actual curve at y prime. So this tangent line passing through x naught, y naught, slope y prime, right? Because our curve y denoted by y here, y equal to y prime equal to this, so slope y prime. So we can compute the slope, actual slope, by the hypothesis. This is fxy, f x naught, y naught. So we know the slope, we know a point on this line, so we know that the equation of this tangent line is y equal to y naught plus the slope y prime at x0, y0 times x minus x naught. So I write better here, so we have y equal to y0 plus this slope is f x0 y0 times x minus x0. So every point living on this blue line satisfy this equation. So now we use, because we said that near this point we can use a point on this tangent line to approximate the point on the red curve. So let's say I will just go a tiny bit next to this red point and use this green point to approximate the point on the soldering curve. So this point, green point here, I call this x1, y1. Okay, now x1, y1 living on this tangent line. x1, y1 on this line. So we have y1 equal to y0 f x0 y0 times x1 minus x0, because x1 y1 belong to this line equals L. Now for the Euler's method, every time you move, you only move 8 units. x1 equal to x0 plus 8, and this 8 they call it the step size, and this one is fixed. For Euler methods, this is fixed step size. So now this, the first equation here become y1 equal to y0 f x0 y0 times x1 minus y1, which is x1 minus y1 is 8 times 8. So you see that we have our first approximation, x1 y1 is x1 is x0 plus 8, y1 is y0 plus f x0 y0 times 8. And with that, you will do similarly, you will approximate the next point. So the next point x2 will be x1 plus 8, y2 now y2 y1 plus f x1 y1 times 8, y1 f x1 y1 times 8. Yeah, this is slope given here, and you do similarly until you get x3 y3. So here I do more. For x3 is x2 plus 8, y3 y2 plus f x2 y2 times 8, and then we have xn plus 1 xn plus 8 yn plus 1 yn plus f xn yn times 8. So in general, this one will be the approximation by the Euler's method. And bigger than equal to 0. Euler's methods.